Welcome back, everyone, to the workshop. I'm Mike again, and I wanted to sort of try to pick up right away kind of where we left off. The question we were concerned with is, when does the Skein lasagna module just vanish for a two-handle body, where the two handles being attached by some framed knot K? And I mean, there was a formula for this Skein module in terms of cables of K, but we were sort of in the middle of thinking about how to simplify it. And last time, which was a bit rushed at the end, so let me try to clarify what was said at the end last time, was that just a single full twist, the tangle for a single full twist in sort of the Kvanov-Brzezinski world can be simplified into some big sum of diagrams with various shifts, with various grading shifts. This delta here means any crossingless n-n tangle. I think I didn't say this last time. That's what delta was supposed to stand for. And this tau of delta was supposed to mean the turnbacks in delta. And again, just if you're sort of not familiar with sort of saying things like this, here's sort of some simple examples for maybe delta to be, I mean, does it matter what I do? I'll do this one. Here's a 4-4 crossingless tangle. And for this, I would say that tau is 1. Okay? So turnbacks here, I guess in some sense, means pair of turnbacks. And that's things like this. Strands that don't make it to the other side. Let me leave some space there. Here's maybe a different one. Okay, that's just the sort of thing. I mean, I'm also going to introduce notation. Sorry, I wanted a 4-4. Okay, there's a 4-4. There's 4-4. A new notation, anytime I have some kind of diagram like this, I can sort of split it into its top half and bottom half. So what I mean by that, I'm going to use sort of this notation. Delta, sort of the top half, in this case, would be sort of this. And delta, the bottom half, in this case, would be this. Okay, and similarly down here, the top half of this would be this, and the bottom half would be this, rainbow. Okay.
Are you reporting also where it, for example, for the delta cap, like, are you reporting where the thing would have ended if you had continued it?
No. The point is that delta is this concatenated with that. And
just as topological.
Just as a topological sort of crossingless tangle, yeah. There's
no labeling on the...
No. I don't care about that. That's right. Okay. Okay. Anyway, so that's just some notation. And again, just to sort of clarify, this symbol is trying to say that each of these deltas I just wrote may, I mean, I know that it does, but from what I told you, just may appear in this giant sum, possibly multiple times. This is not like a sum over each specific delta, you know, like maybe multiple times. Okay, and always with a shift in this range. Okay, that's what this notation is trying to say. Okay, so that's what the notation is trying to say. This is essentially then where we left off last time. And from here, I want to do some more messing around with some symbols. So a sort of nice, easy one-liner exercise would be, now if I want to take k full twists, all sort of concatenated together, okay? Well, if I know what to do with one, I know how to induct, basically. And you learn that the shifts are now go up to 2k minus 1 times the turn back number. Okay, and now I want to sort of finish the story. So in the cabled formula, the cabled Kolonov-Rosansky formula for computing the Skein modules, you have, like, your formula depends on terms like this, in the way we were writing before. Okay, that's that picture, as we said last time, that's just a picture for cabling K with N strands. Okay, and now, but I've just decided that this twisting part, this framing twist, can be simplified like this, so I'm just going to do that. Okay, let me do that here. This isn't really simplification yet. So this bound I'm going to stop writing of delta. Tau always depends on delta. And I've now drawn delta as its top and bottom halves. Okay. Okay, and now here is sort of, I guess, I wanted to sort of show all this because somehow when you're doing these sort of combinatorial link dynamics, like a very large part of what you're often doing, especially because you're dealing with cables, is just this very simple idea that any turnbacks that are actually appearing here, I can just pull and sort of drag through the cabled K. Okay? And when I do that, this part is just the blackboard framed cable. In particular, there's no twisting in here. I only use Radermeister 2s. In other words, this is sort of a framed move. Okay, so I incur no shifts while doing this. So think about what that means. Sorry, this is supposed to be a sum over such things. So now I sweep that around, and now I have something that looks more like this. And I've gotten rid of 2 strands for each turn back. Okay. Okay. Okay, and so now each of these guys is some, I mean, this is just a link in, well, a link diagram in R2. It has some associated homology group, and I'm sort of checking what's the maximal possible M grading in that group. Okay, and I'm going to show that these maximums have to die as the cabling goes to infinity. That's what we're doing. Okay, so each summand here has sort of a maximum non-zero M grading. Let me make sure I give myself some. Okay, well, sorry. Well, there could be, at most, this kind of shift. Okay, and then whenever, like in here, I have some turnbacks facing downward and some turnbacks facing upward, they might, or they might not, combine to make disjoint circles. Disjoint circles can be given, well, each disjoint circle can shift this more because a disjoint circle has Kolanov homology with a 1 and an x, and the 1 has a positive M grading. Or, sorry, the x has a positive M grading in Kolanov-Brzezinski. So there might be up to tau circles here. So this term came from disjoint circles. Okay, possibly. And then I'm sort of left with, whatever maximal z grading there is in this picture. Okay, but this picture is a little bit deceptive because it may be that after I've swung the turn back around like this, it does not hit this turn back. It keeps swinging around, right? So there may actually be more things deleted here. Yeah. What is the z grading? Is the sum of the quantum and homological gradings. Or, oh, I'm sorry, M is supposed to be, Z is supposed to be M. An earlier draft wrote Z, and then I remembered that we use Z as sort of, Z is either Kolanov-Brzezinski or Lee-Brzezinski. So, sorry about that. Thanks. Yeah. M for mixed grading. Yes? Oh, okay, this changed, right? Okay, this changed. Yeah, the question is, was this supposed to change or what happened? This changed because essentially I took this picture and swung it through the knot, and now it's down here. Okay, that's sort of, the main point, I guess, of all this. So yeah, make sure you understand that like somehow you can take turnbacks and swing them through, and that's equivalent to just taking this picture and swinging it through. Okay. Yes, there could be differentials going all sorts of ways. I don't care. In the end, I'm just asking what gradings can have non-zero things, and so the differentials, whether they're killing more, I mean, if so, that's great or not great. But no, yeah, that's sort of the magic of this. So maybe, yeah, a thing to say is I chose to sort of show you all these sort of simplifications for the vanishing results, because when we do the vanishing result, we can ignore the differential. And it's easy to show. When you want non-vanishing, we're still going to be able to, well, you'll see later. Anyway, all right, so now, okay, there's a minus tau and a plus tau. That's very nice. Okay, so do I have a specific way I'd like to write this? So there's a minus n. There's the k has a minus n and a minus 2 tau. Well, so that's just some arithmetic. Here, I do need some way of understanding what the maximal m degree is here. Okay, and so now, you know, let me just write it, and then I'll try to say what this is. So I claim that there's a bound on this, okay, that depends on this. Okay, how do I want to say it? I want to say it is oops. So this bound is due to Lenny Ng. And he usually writes it in terms of Thurston-Bennington numbers, but I wanted to present it to you this way because when you write it in terms of Thurston-Bennington numbers, it makes it sound like contact geometry was involved. And I claim that, in fact, the bound itself and the proof of the bound involves no contact geometry. Okay? The bound really is that this maximal grading is bounded by, for Kolonov-Rosansky, you have to like do some mental gymnastics from the usual Kolonov. It is the number of, okay, so all zero resolution means you take all the crossings and you take the zero resolution. In Kolonov-Rosansky, that means this crossing turns into this. Okay? It's the opposite of the usual Kolonov conventions. So this would be the all one resolution of the usual Kolonov. Okay? And then in that picture, the resulting resolution, you just count how many points of vertical tangency do you see? And that's, you know, if you're doing Legendrian things, that means some kind of cusp rather than a vertical tangency. And that's how you start to see TB come into play. Okay? And I mean, I'm not going to prove it for you here. I just really want to emphasize that the proof is, again, purely diagrams, combinatorics. There's no reference to any geometry at all. Okay. I just mean a place in the picture that has a vertical, where the tangent line is straight vertical. Any circle must have at least two such points, but circles may have more, right? But any crossing like this ends up contributing potentially no such points. But the other type of crossing contributes two such points. That's it. Yes, okay, so the complaint is that a vertical line has infinitely many such things. Yes, if your picture has straight lines, you know, maybe the correct claim is generically, you can arrange to have sort of finitely many things. Minimum over, well, I guess I would claim if you have a straight line somewhere, you should make it a little bit bent, okay? The bound as written, like the proof does use sort of the fact that you may see things like this, and you should count, like, well, like you should count if you have some twists and turns like this. But I mean, there's a bound, right? Then, you know, sort of, you're going to be, well, let me leave this here and say, you know, somehow, if you want like a very precise version, read Lenny's paper. Okay, this is the essential idea. And what's important, a very important thing about such a bound, okay, is that it's linear in the cabling. Okay, so okay, let's finish up here. An important thing about when you cable with blackboard framing, so with no extra twisting of any sort, then the number of such tangencies, if you allow me a little bit of wiggling here, okay, is just how many cables were there compared to the original knot. Okay, you have to think a little bit about what happens when you resolve giant cables of crossings, but I claim you can do this. And so now you see that, okay, well, this thing is going to go to negative infinity as n goes to infinity, as the amount of cables goes to infinity, as long as this k is sort of beating out whatever this number is. Okay, so this is the argument. And so I want to present it now as it's presented in the paper. Okay, but yeah, so the overall argument, the maximal grading available becomes negatively infinite, and thus you're going to see nothing in that grading. You're going to see nothing in that limit so long as the twisting amount was more than the number of vertical tangencies. The twisting amount is not literally the framing because I ignored the writhe while doing this. So once you put the writhe back in, writhe together with this, at least in the case of Legendrians, so if Legendrian, well, no, let me not write. Let me just present the you have to sort of work through what exactly sort of Legendrian thing you found here, okay? But I claim it's negative max TB of the mirror. And I also claim that the proof that I've showed you would work exactly the same way even if there was a link in the boundary, no matter what the link is in the boundary. Okay, and it can be sort of an exercise to sort of convince yourself of this. Okay, just, you know, a link in the boundary just would mean that in addition to this cabling of K, there's also some link, like, in that picture. But it is not being cabled, and it's nothing about it is growing. So somehow it's going to contribute like some kind of constant term to this limiting. Okay, so this is sort of the vanishing result, but there's actually a little bit more to it. Once you believe that this is true for any link in the boundary, you can also show that if such a two-handle body embeds into some other four-manifold, then the lasagna for this four-manifold must vanish as well. Oops, that's supposed to say such. This is like video recorded, is that right? Yeah, and if you can have some links in the boundary here as well. I'm not going to write this. Somehow, that's some kind of, yes, if x has some other boundary, sort of disjoint from what was originally the boundary of xk. I'll draw a picture just to sort of, the picture is related to the idea of a general sort of gluing statement, which we haven't really said yet. I'm going to try to say something about it later if there's time. But essentially, this is sort of the statement that if here is x, and like xk was sort of embedded into it, any Skein could have been isotoped so that it sort of intersects this boundary transversely in some link, and then you have to sort of say something about, okay, it could have been realized from some Skein in xk together with some kind of gluing principle. I hope to return to this with the Lie version, so let me not say more than that here. Once you have something like this, here's a great exercise. Well, great in the sense that it's very important if you want to detect exotica. S2 cross S2, therefore, has 0 Skein lasagna. Let me just mention this sort of recovers work of Ian and Melissa, who you guys have all gotten to talk to. So they had a separate proof of this statement, but this is our version. Okay. Okay, we're going to move past this. Yeah, sorry. So yeah, so a couple people have asked this. If there's extra links, oops, I've somehow, oh yes, that's right. If there's links on the boundary, this doesn't really affect the statement. I mean, in this picture, that's just any Skein now has to have touch the link here. Okay. Okay, so now I really want to try to spend some time with the Lie version of all this. Okay. So yesterday and the first half of today was sort of vanishing. The rest of today will be about the Lie version as opposed to the Kvanov version. And the Lie version will allow us to show sort of a non-vanishing statement tomorrow. That's the plan, at least. So uh, so so I don't. I mean, you're sort of forcing large framings here. Uh, so can you get something negative definite like this? I don't think so. Uh, yeah, I think. Is that right? You're always going to have a B plus. Is that right? I mean, yes. Whereas, but I don't know. Maybe we should return to it later and try to get precise about it and have to sort of think about it. But yeah, so somehow this is some kind of statement about large framings. In particular, the non-vanishing statement is going to be a statement about very negative framings. Okay. Okay. So to talk about the Lie version, let me first just try to quickly recall what is the story for links in S3. So for a link in the 3 sphere, let me, I think earlier Melissa wrote KHR superscript Lie. Let me write LHR. It's just a handful fewer symbols. Everything over the rationals. Okay, I'm not going to keep writing. Everything I write is going to be about we are working over the rationals. The Lie homology is always generated by one summand for each orientation of the link. Okay, it's sort of a very, in that sense, it's a very boring theory. Okay, this L sub O, I'll call a Lie generator, and the proof is constructive. You hand me an orientation of the link, and I can sort of find a very specific chain group element that then descends to homology and show that it's non-zero, and then I show that this is everything, and none of them are the same as each other. Okay, so the corresponding statement for the Lie lasagna, okay, is a little bit different, but you'll see how the orientation sort of comes into play here. I'm going to write the statement, and I'm sort of emphasizing it now, specifically for no link on the boundary. Okay, there's a similar statement for links on the boundary, but it takes a little bit more words to say. The Lie lasagna for a 4-manifold is always generated by, so we use the notation x sub alpha plus alpha minus, where alpha plus and alpha minus are just second homology classes. So there's one for every pair of second homology classes. Okay, and so okay, I think we're not going to have enough time to draw the real gluing thing, but so what you should think about is this. You have alpha plus and alpha minus both in H2, and No, these are just sort of independent now. So there's like infinitely many typically, and yes. Okay. Yes. Okay. So I just want to give some indication of what this lead generator is supposed to be in the lasagna. Okay, so basically, let's see. Based on what do I want to say? Okay, so these two homology classes, I can represent them by at least immersed surfaces, okay, oriented. Okay, but when you're doing this lasagna business, immersed is as good as embedded because you're always allowed to puncture and put input balls. Okay, so place input balls at any intersection point. Okay. So if you have any, you also need to puncture every component of your surface. This is, let me not say too much about why, okay? And now, so you have some kind of, maybe I'll draw, let's see. You had some surface, sigma plus, and you had a sigma minus. Maybe they intersected in places, so anywhere they intersected, I puncture so that I really have sort of my embedded thing now. Okay. I also puncture each piece. Okay, so now I have maybe a bunch of input balls and input links on these things, right? And so on each input sort of like the boundary of sigma plus is various input things. Okay, I hesitate because this single input ball has the input link has components from the boundary of sigma plus and from sigma minus. So I don't want to write all that. Just the boundary of sigma plus. That's some link in the 3 sphere, and I have an oriented surface, sigma plus, that tells me how to, what an orientation of that boundary piece, and I can, that allows me to decide a lead generator there. Okay, that's for the sigma plus. However, the sigma minus, okay, on each boundary of sigma minus, okay, you do the same thing except you use the opposite orientation. Okay, so this just statement sigma plus minus, or like alpha plus and alpha minus, is just a way of saying which of these oriented surfaces are you viewing as having its sort of given orientation, and which of those are you viewing as having opposite its given orientation. And you also there are some units here that I'm trying to ignore, okay? You multiply by some power of -1, and you multiply by some power of 2. Okay, this power of 2 is sort of very important and sort of indicates why we really need to be working over a field of characteristic not 2, and the whole thing is sort of much more complicated over F2. Anyway, I mean, that is all kind of the same as in the usual Lie homology scenario. And so the sort of old story is yeah, okay, so this isn't a proof. This is just how you build a generator, okay? So, and the proof that you're getting the right thing is, you know, there's some real work involved, but yes, there's some kind of statement that none of the choices here, I mean, there's many choices, and other choices give things that are actually equivalent in the Skein lasagna module. There are relations that will relate these things, okay? But I'm sorry, I just don't have sort of the time to sort of say more about it. But yes, there's work there for sure. Okay, so do I want to, sorry, I've lost, is there, yeah, let's say it. So for links in S3, the Rasmussen invariant, originally just done for knots by Rasmussen, but the generalization to links was handled by Belyakova and Verley, and it's essentially, I'm going to put an upper R here. That just means in the Kavanagh-Brzezinski conventions, as opposed to the original conventions handled by Rasmussen. And this is, I think, I wrote this. Melissa, is this what you call like the filtration level, the filtered grading? Okay, the filtration level of you know, the Lie homology is generated by all possible orientations of the link. But in the beginning, you were handed an oriented link. So there was some original orientation also given to you. The Rasmussen invariant is the filtration level of that orientation. It's some integer. Okay, and our version of this, of course, is, let me just say, for the Skein lasagna modules, okay, the Rasmussen invariant is the grading, or sorry, the filtration level of essentially the case where, like if you look at that picture, sigma plus and sigma minus, it's all sigma plus. So you're using entirely the orientation given, so to speak. You're not flipping orientation anywhere, which is also what this is. Okay, and just to sort of, you know, as a thing to emphasize, you know, this thing was built out of filtered groups, but there were sort of infinitely many relations. The relations can push the filtration around. And you can have non-zero Skein module terms that nevertheless have negative infinite filtration level. Okay. In fact, I'm sort of out of time. Let me just say quickly, the vanishing result that we proved earlier is also saying that if I do the Lie Skein lasagna module for these very positively framed two-handle bodies, all the filtration levels will be negative infinite. Okay. But anyway, let me stop there, and tomorrow we'll pick up on, what sort of properties this has, and most importantly, how can you ever hope to compute it? Thanks. So I think we have time for maybe a couple questions here if there's. The question was these lead generators on the input balls. But the answer is yes. Each input ball, the link there is just the intersection of the surface with that input ball. I just wrote it as the boundary of the surface. And yes, that is the link in S3 and these various S3s that you were assigning a lead generator to. Well, yeah.
But where does the filtration grading come from in the lasagna as opposed to like in?
Where does the filtration grading come from in the lasagna? Well, it's sort of a general statement that any sort of Skein lasagna module that you build in the way that we have been building will inherit certain properties, or whatever you want to say, certain aspects that the original sort of link homology theory had, in this case, including the filtration. So, I mean, it's some kind of, the filtration grading here is some sort of minimum over all possible fillings that are equivalent to your guy of some combination of the filtration levels of all the input balls together with some further shifts because, the surface should be doing something. Okay, the topology of the surface also contributes somewhat to this. But let me not maybe say the details there. Yeah. Oh, okay. Okay, great. Okay, well, oh, yes. Yes, yes. So the question was, if my four-manifold is just the four-ball, okay, and then my links on the boundary are really just links in the three-sphere, do I just straight out recover the original things? And the answer is yes. Oh my goodness. There is an extra shift involved just because of the way we've defined it, because I must apologize. Everyone, I missed a symbol. There's an extra shift. I apologize for this. There's an extra shift in the original definition that I always sort of forget about that we did not include here. But yes, and this is actually sort of, again, a sort of general statement. If you have certain properties of your link homology theory, you can guarantee that on the four-ball, the Skein lasagna will just recover the original link homology theory. Okay. Yes. Okay. I think maybe we should sort of cut it there. We can sort of course, talk more outside and other places. But let's end this one here, and we'll resume at 10:30. Thanks.